by taking questions from the homework. So last time we assigned 1 through 12. Obviously, it's not due today. There's no reason it needs to be done today. Remember, the due dates for the homework are Sunday at midnight. But if you had encountered something you had a question about or weren't sure about or wanted to talk more about and get some more feedback on or whatever, happy to do that now. The point of the homework due date being set out front, like so far ahead, is that you have opportunities to do this to like get some feedback before we move on. Grace, I saw your hand. Yeah, sure. Just grab this. So for number one, yes, of course. For 1 through 4, what I'm really going to want to try to be doing is either use the form it's currently in because there's something obvious I can take advantage of, or maybe I want to just translate this to a different form so it's easier for me to evaluate whether it's a function or not. So for number 1, you could think of, hey, no matter what number I put in for x that's greater than or equal to 5, when I take the square root of it, I'm going to get an answer. So like the domain is covering everything. And when I take the square root of something, I only get one answer for that, right? Like the square root of 7 isn't 2 numbers, it's just one number. You know what I mean? So again, those x's are only going to one place. Or you could say, okay, well, like I graphed this thing in my calculator, and it looks like this, and that passes a vertical line test. Totally reasonable explanation as well. Does that, Grace, are you okay with those?
Yeah, so all we have to do is plug it into our calculator?
Well, not all of them you can plug into your calculator. So like 2 that has a plus or minus, can't plug a plus or minus into your calculator. And 3 and 4 are formatted in the wrong way, so you'd either have to rearrange them or think about it in a different way. Is that okay? Okay, so 1 was quite easy because it was one that could easily just be, I can just plug in my calculator, I don't have to do anything.
Will you do number 2 then?
Sure. So 2 you couldn't plug into your calculator, right? Everybody agree with that because of the plus or minus? So what I would do instead on something like 2 is I would just say, okay, well, what if I just pick some values for x and see if I get, how many different, if I get one value for y or if I get more than one value for y. As soon as I get a situation where I get more than one value for y, I'm done because I know that it's not a function. If I consistently get one value of y, then maybe it's like, okay, so it seems like this is a function. Let me think about it a little bit more carefully rather than just picking arbitrary x values and think, okay, what is going on here? Could I be a little bit clever about the x value I choose and maybe get more than one y for that answer? But we don't have to think too hard about 2. So if I just pick, say, x equals 0, you have y equals 0 squared plus or minus 1. So that just becomes plus or minus 1. So y would be -1 or +1. Is that okay? Now there's a situation where you're getting 2 y's for 1 x, right? Basically what you have is this kind of a mapping diagram, right? Is that okay? So that's not a function, you're done. So you just be like, look, x equals 0 goes to 2 y's. I'm done. Looking at the other ones quickly, I don't think you'd have too much of a problem with the other ones. they should be relatively straightforward using one of these two methods of either generating a graph or, picking some x's and looking for a situation where you get two y's. But that's really all we're doing, is we're hunting for, some evidence that it's not a function. Anybody else on the homeworks, Alyssa? 10? Sure. So that's x minus 1 over the square root of x. I don't remember what it is, if it's x or y or, I'm sorry, f of x or y or some other function. Doesn't really matter though, right? So here we're asked to give the domain. Since this is context-free, like there's no story problem built around it, I know the implied domain is just all real numbers. To figure out the relevant domain, I'm going to look at the operations involved. So I see 4 operations, right? No, 3 operations. I see subtraction, division, and a square root. Now, subtraction of real numbers, I know there's no issue with, right? For a square root, I know that I can't have negatives. And if I have division, I know that I cannot equal 0. You guys agree with that? Alyssa, are you good?
Yep.
Okay. Now, I'm going to be a little bit clever here. So if I want to solve for the square root of x, I would just square both sides, right? Good with that? If I combine these two together, since it's an and statement, if x is greater than or equal to 0 and x cannot be 0, that's just the same as x has to be greater than 0, right? Is everybody okay with that? I'll take your silence as yes, you are okay. If you're not, speak up and we can talk some more about it, but at that point, it should be easy to generate the integral then. Yes?
So we can have 0 in the root, so it's parentheses, but then in like number 9, it's the square root of x minus 1. I thought it would be x has to be greater than 1.
Greater than or equal to. You can have 0 in a root.
So you can't, okay.
Yeah, the reason we couldn't, and again, like when I wrote this, that was reflected here, that 0 is okay to take the radical of.
Oh,
That problem was because they also had 0 in the denominator, so that was why we lost the bracket on that particular problem. Is that okay?
yeah.
Okay. Josie, I saw your hand as well. Did you have
Same one.
Perfect. Okay. Again, this is not the last opportunity to ask questions about these things. The homework due date is Sunday. We'll see you guys again on Friday. So if you get further and you have more stuff, or you're like, hey, I went back and thought about this thing after blah, 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 I wanted to ask that, totally okay to do that. But it looks like it's time to just kind of get started with the next set of stuffs. Okay? So let's roll. Section 1.4 is about increasing and decreasing functions. Okay, so this again is a topic that we should have talked about in our in our Algebra 2 class last year. If you don't quite remember that, that's okay. We'll review it again today in good detail. But for many of us, this will come as another review idea. So we'll just start with a couple of definitions. So we say that a function f is increasing if for any 2 points on the interval a positive change in x results in a positive change in f of x. And to conserve my writing, the definition for decreasing, we just change one word. We just change from a positive change in f of x to a negative change in f of x. And we can also have constant intervals. And again, the only change there we make is from positive to no. So I'm going to write 3 definitions that way, just conserving some pen, or me having to write some stuff down. If you want to recopy that stuff 3 separate times, that's fine, no biggie. I'm not going to do it that way because yike-a-rooskies, that's a lot of letters to copy down where it's basically the same thing 3 times. I guess I could have just done the lasso and then edited those 2 words 3 times, but whatever.
So if you're decreasing, if one is positive and one is negative.
So there, what we're saying here is, and I'll draw some pictures here to kind of reinforce what the definition is saying, because from our standpoint, what I'm going to be asking you to do, the definition is not that terribly useful to us. I'll give you kind of like a visual of like what it is you're looking for. That'll be much more useful when it comes to it. But I'll explain how the visual is equivalent to the definition here in a minute when I draw some pictures. So if you want to hold on that, I think I'll clean that up and it'll make sense in just a minute. But I know the definition is a little wordy, right? So let's say we have, some graph that looks kind of like this. Okay. The way to think about increasing, decreasing, and constant, I think the simplest way is to imagine you have like a little person that's walking along the graph. And they're always walking from left to right. So you have like a little person. This first section is uphill, right? If you're walking along that part of the graph, it's uphill. Uphill is increasing. So John, when we talk about a positive change in x, what we're saying is as you move from left to right. So if you take, like a point on the right, and you subtract its x-coordinate from the point on the left, the change would be positive. If you then subtract their y-coordinates in the same order, that change should be positive. Basically, if you take the 2 points and you draw a straight line, it's a positive slope. So we're walking uphill. This middle section is flat. That's constant. So again, if I pick 2 points and I take the point on the right, its x-coordinate, subtract it from the point on the left, that's a positive number. If I then subtract the y-coordinates in that same order, it should be 0, right? And in the third section, our little person is going downhill. So that's decreasing. And again, if I take 2 points from that section, if I take the point on the right and subtract it from the point on the left x-coordinates, it's a positive value. If I subtract their y-coordinates in that same order, it should be a negative because we're going down. Because the point on the right is lower than the point on the left. You know what I mean? So the part about a positive change in x just means that we're always going to take, we're always reading from like left to right. Does that make sense? So the definition is kind of wordy, but like when we think about it visually, it's like, oh yeah, it's a pretty simple idea. Uphill is increasing, flat is constant, downhill is decreasing. Not a big deal, right? Okay, so let's give these coordinates. Actually, let's call that some values there. So let's say that's negative 2, 3, and positive 2, 3 are those 2 points. And when we describe an interval over which, since that's what these constant or increasing, decreasing are referring to as an interval, when we talk about these intervals, we're describing like the x-coordinates. Yes?
What's that arrow on the bottom of the uphill slope? What does that make it like decreasing in the opposite way, or does it not matter?
So when we talk about increasing, decreasing constant, it's always in reference to from left to right.
Okay.
Always in reference from left to right. In fact, everything we do when we describe graphing in mathematics is always with the assumption you're moving from left to right. Does that clear that?
Yeah.
Okay, yeah. So you're right. If you allow us to read in any direction, then like what the heck does that mean? Increasing, decreasing constant has no reference, because if you go one way, it's one thing. If you go the opposite way, it's the opposite thing. But it's always from left to right. Not necessarily like the other way of thinking about it that sometimes students want to do but is not correct is like, okay, if like I poured water on top of it, like which way is things going to run? Like if you do that, then the left is like, oh, things would run down, and to the right it would run down. But no, that's not the way you want to think about that. So it's just like as a straight line from left to right. Is that okay with everybody? Okay. So our increasing, again, we describe this always with x-coordinates. Our increasing begins here at the far left end of the graph, correct? As we move from left to right, that's the first place we begin increasing, because we've contains the left-hand arrow, the lower bound for that interval should be negative infinity. And we stop becoming increasing at negative 2. Everybody good with that? So the upper bound is going to be negative 2. And for intervals of increasing and decreasing, the ends are always parentheses. The reason it's not a bracket, say at the negative 2, is because of the definition, because you can't pick a point to the right of the negative 2 that still ends up with an increasing result. If you do that, it's, like you pick something to the right of 2, it's going to be constant now. So 2 can't be included in the increasing set, if that makes any kind of sense. The next section we get to is the constant section. Well, let me do some color coding. So the constant section begins here at negative 2 and ends here at positive 2. Again, only referencing the x-coordinates. When we describe our intervals, we don't care about y's, we only care about x's. Well, I shouldn't say that. Intervals of increasing, decreasing, constant, we only care about x's. If you're writing an interval for the range, you care about the y's, but let's try to be specific, right? And then my decreasing starts here at 2 and then goes all the way to the right. Since we're containing the right-hand arrow, that would be positive infinity. Do you guys feel okay about that? Ish? Kind of? Maybe? Let's do another example that's a little bit more complicated. Since this other example is a little bit more complicated, I'm going to draw the graph not by hand, but rather like I'm going to generate it digitally so that it's a little bit clearer what's going on. So if you just give me one moment while I get that formatted the way I want it, it'll just be like one more second. That'll do. Okay. Oh boy. Okay, so let's say that we have this graph. Now, imagine that any place where the graph is leaving the window frame there, basically there's an arrow at the end of it, right? So you have like arrows in all those locations. Hopefully that seems probably obvious, but I just figured I'd want to state that. Let's take a look at this. How many sections of the graph do you see are increasing? Go ahead, sir.
2.
2. Good. So if we start at the far left, this section is all going uphill, correct? And if I look at the middle, if I start here at the farthest left point and I go up to 0, that's also increasing. From there, if I start at 0 and go to the right, that section is decreasing. And if I start at the top here and go to the right, that section is also decreasing. Everybody feel okay with that? So if I write my intervals then for increasing, the first piece starts at negative infinity and goes to here, which if I look down, looks to be negative 3, is the x-coordinate there where it stops increasing, because there's an asymptote, so it has to stop, right? And then because I have a whole separate section that's increasing, I'm going to use the union. And that increasing section starts down here, again at negative 3, and goes up to here at 0. My decreasing sections, well, the first decreasing section starts here at 0. And goes here, which looks like positive 3. Then I'll do a union. The next decreasing section starts there at positive 3 and goes on forever. So I have positive 3 to infinity. Feel okay there? Okay. The next thing we'll talk about in this section is this idea of extrema. And there's two types of extrema. There's maxima, which is just the plural for maximum. And then there's minima. Minima. So a maximum or a maxima is the so it's the value of a function. We'll call that value f of c. That is greater than or equal to all of the other range values or y coordinates, right? On some interval containing C. Oops. I'm going to say, yeah, that's fine. A minimum, or the minima, is the same thing, except instead of greater than or equal to, it would be less than or equal to there. Instead of doing the color-coded definition, I did the copy and paste. Just changing the thing up, practicing my OneNote skills with a Z. Skills. Does that feel okay to you guys? Now, there are two different types of minima and maxima. So there's global or absolute, and then there's local. So we say a maxima or a minima is global if it's actually the biggest or the smallest for the entire domain. So if you look over the entire domain, if that is actually the biggest y coordinate for the entire domain, that's an absolute or global maximum. Or it's tied for first. There could be lots of absolute maxima. Everybody's okay with that idea? It's local if I look from this interval, it's the biggest, but if I expand out here, there's something bigger than it yet. And we'll do a pictorial example here in a second to kind of illustrate that. Actually, let's just go look back to here. Yeah, that'll be good. So this point here is a local maximum because, from -3 to +3, that's the highest point. But if I expand out to like -6 to +3, like certainly that point is higher. You guys get what I mean? Now, this graph has no global maximum because, oh boy. Has no global maximum because I have an arrow pointing up. And has no global minimum because I have arrows pointing down. Everybody's okay with that? So there's always a point higher than any point I name and always a point lower than any point I name. Does that help a little bit with the difference between local and global? One of the things I'll ask you guys to do is be able, if I give you a function, to be able to find those extrema and label them. The tool that we're going to use to do this, though, is our graphing calculator. So let's run through how we do that on the calculator. If you have your graphing calculator with you and you'd like to follow along, you are welcome and encouraged to do so. If you don't have your graphing calculator with you, that's okay. It's not a big deal. You can just kind of sit and watch. That's fine. If you're like, yo, I need to practice that stuff, you can always load up the video of the lecture and go to this part and walk through the calculator steps on your own with it when you have your calculator with you. Okay, so first things first, we're going to turn on our calculator. To find these maximum or minimum, or find the maximum and minimum, what I'm going to need to do is I'm going to need to look at the graph. So the calculator needs the graph in order to find the maximum or minimum. So the first thing I want to do is to graph this function I've given us. For example, to graph anything, we press the y equals button, which is in the upper left-hand corner. Before I start typing in something, I'm going to go through and clear out any other functions that might be typed into my calculator. Since it's been a long time probably since I've used my graphing calculator, I'm going to actually scroll all the way down to the bottom and make sure I don't have any gobbledygook at the bottom because I left the calculator in my backpack with the cover off and like random buttons got pushed. You'd be surprised how often that happens. And then up at the top, I'm going to check where it says plot 1, plot 2, plot 3. I don't want anything highlighted. So if I see something like this where plot 1 is highlighted, I'll just use the up and down arrows to move my cursor up there and press enter to unhighlight it. So nothing should be highlighted at the top. And then I'm just going to type in my function exactly as it appears. So the X is right there next to the green alpha button. The exponent button is right there above the division symbol. And then everything else is just like on the basic keyboard there for the calculator. So I'll just take a minute and type that bad boy in. Okay, once I've got this thing typed in, I want to graph this, but it's probably been a long time since I've used my calculator. I have no idea what the graphing window is set on, or if it's even going to give me a decent picture if I press graph right away. So what I'll do instead is I'm going to press the zoom button and pick Z standard. Yes, sir. Of course. And that'll choose the normal -10 to +10 viewing window. So I should get a decent picture for a problem like this. Or did I type something in wrong? 2, -4, -3. Okay. Oh, I typed -1 instead of +1. I did this already today, and I was like, that's not the same thing I had last time. I just had a typo in my formula. Oops-a-daisies. Okay, so this is what your graph should look like then, right? When I look at this, I see one global minimum right here where my mouse pointer is. I see one local maximum right here where my mouse pointer is. And I see one local minimum right there where my mouse pointer is. And I see no global maximum because I have arrows pointing up. Everybody happy with that? So I'm just going to make a spot for each one of those values. I'm going to go ahead and write none for global maximum. And I just like to write them in the order that I see them on my graph so that I don't accidentally put them in the wrong spot or something. You know what I mean? Everybody's happy with this so far? Okay. So the calculator can find these minimums and maximums for us with a tremendous amount of accuracy. To get those values, what I'm going to do is I'm going to press the second button. That's the blue button at the top left. And then the trace button, which is the fourth button on the top. If I look at those commands, if I'm looking for the global minimum to start with, which one of those commands looks the most promising? Minimum. Yeah, you're right. So I'm going to go down and pick the minimum command. If I look at my calculator screen, the calculator is now asking me a question. It says left bound. So what it wants me to do is take my cursor, which is located right there, and move it so that it's somewhere over here on the left side of that minimum. So I'm just going to use the left arrow on my keypad to move my cursor so it's somewhere over here. It doesn't really matter where it's at over there. It just has to be somewhere. And then I'll press enter. Next, it asks me for a right bound. So I'm going to move my cursor so it's somewhere over here on my function. Doesn't really matter where. I'm just going to press the right arrows until it's over there. That looks good. I'll press enter. Now it asks for a guess. As long as we're picking a pretty narrow left and right bound, so the only extrema in there is the one that we're looking for, the guess doesn't matter. So I'll just press enter and save myself any button pressing. So there it gives me the x and y coordinate for my global minimum. I'm going to just round that to 3 decimal places rather than copying all those decimals, although I could if I wanted to. I just don't, you know. So there's my minimum. Is that cool? Okay, let's find the next one, the maximum here. So again, second trace. This time, though, I'm going to pick the maximum command. The calculator is going to ask me the same 3 questions, left bound, right bound, and guess. So I'm going to take my cursor and move it somewhere to the left of that maximum, so like right in there. Oops, 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 oops. That looks good. And then for the right bound, I'm going to pick somewhere like right over here. That looks good. The guess doesn't matter. And then I'll copy that point down. Once you guys try to find that last local minimum on your own, plug that through. I'll write down the answer right now so that you can see what it is, so you can check your own stuff. Again, not a hard process to do, but yes, sir. Yeah, are you thirsty or what, my man?
Yeah.
Did we get it? Those of you that tried to do it on your own, I'll take your silence as an affirmative. So not only have I answered the question of where are the extrema, I can also write down my intervals of increasing, decreasing from this just the extrema listed here. So let's show you how I can do that. So because I wrote my extrema in order from left to right, so I know that the first thing I'm going to encounter is my minimum, right? So from the left going down to the minimum, I must be decreasing. Everybody agree with that? If I'm starting at a minimum, I have to start it up high and then I'm going down to a minimum. Agreed? So that first part of my graph is decreasing. So negative infinity to the x-coordinate of my first minimum should be in the decreasing section. Then I've gone from minimum to maximum. So I've started somewhere lower and I'm going up to somewhere higher. So that means that next section needs to be increasing. So starting at the global minimum and going to the local maximum, I'm increasing. Okay, so now I'm at a global maximum. And the next place I'm going is to a local minimum. I'm sorry, local maximum to local minimum. So again, I'd have to be decreasing there. Does everybody buy that? So I'm starting from a maximum, going to a minimum, have to be going down. So I'm going to be decreasing there. So I'm going to go from the maximum to the minimum. And now I'm at a minimum, and I finish out my graph. So the other half of a minimum has to be going up, right? So that should be increasing. So just to kind of color code this a little bit at what we did. So for a continuous function, the boundaries, the bounds of my minimum, or my intervals of increasing and decreasing, are my extrema, right? A change in increasing to decreasing has to be at an extrema, provided I have a continuous function. If I have something with a discontinuity in it, you can also change from increasing to decreasing at a discontinuity. But we had a polynomial here, right? And all polynomials are continuous functions. So excuse me. Does everybody feel okay with increasing and decreasing and extrema and the relationship between them? Okay. We'll talk next about section 5. I think that'll be the only, or the last thing we get to talk about today. I think just 2 sections today. So these, in section 5, we're going to talk about types of symmetry. So like increasing and decreasing, which are descriptors of a function, right? They describe some characteristic of a function. Symmetry also describes a characteristic, or describes characteristics of a function. In this class, we're going to talk about 3 types of symmetry. So I'm going to abbreviate the phrase with respect to as WRT. With respect to, I'm going to abbreviate as WRT. So let's say we have the function x equals y squared. This is an example of something that's symmetric about the x-axis. Basically what this is saying is if I pick some x value, the distance from the x-axis to the function is the same on either side of the x-axis. That's basically what we're saying. Algebraically, what this says is that f of x should equal negative f of x. Yes, sir.
If it were the other way, like y equals x squared, would that be f of x equals f of negative x?
Yes. That's a different type of symmetry, but yes. And again, what we're saying here, this is like, let's just call this x value here b. So this is the point like b comma a. And this is like b comma negative a. So f of b is equal to a. And negative a is also equal to f of b, right? That's kind of what we're saying there. And this is going to be important when we prove these symmetries. Not geometry proof where we're writing like two columns, but like algebraic proof, like when we prove two things are inverses. The second is symmetry with respect to the y-axis. And the example I'll use here is basically the one that John had suggested. So if I have y equals x squared as my function, I know then that f of negative x is equal to f of x. Oops, we usually write it the other way around. That f of x is equal to f of negative x. And again, that relationship will be important. This type of symmetry with respect to the y-axis, we also call functions that have this symmetry even functions. I don't know why I'm still minimized here. Give me the whole thing. So that's equivalent to saying a function with symmetry with respect to the y-axis is also an even function. So those two statements are equivalent. Even function is probably the more common one because, boy, that's a lot less letters to say. The last type of symmetry we'll talk about here is symmetry with respect, sorry, not symmetry with respect to. It's 180-degree point symmetry with respect to the origin. So example of what that looks like is something like this. So y equals x cubed is our example. So basically what I'm saying with 180-degree symmetry So if I take this point here and like send it 180 degrees around with respect to the origin, I end up with a point over there, right? That basically one side of it is like two reflections, like reflect across the x and reflect across the y, and you get the other half of the graph. So what we say here is that f of negative x should equal negative f of x. And this we call functions with this symmetry, we call odd functions. And again, that's the preferred descriptor rather than 180 degree point symmetry about, or with respect to the origin. It's just calling it an odd function because that's a lot less words. Let's look at some examples. Oops. So just again, to remind us, I'll write down our main tool here to prove that a function is odd or even. So for A, I'm going to start in either case by figuring out what f of negative x is. So I'm going to plug negative x in for the x's, which gives me this, right? Is everybody okay with what I did there? Now, if I take a negative and raise it to the fourth power, what am I going to get? Positive, because 4 negatives multiplied together is a positive, right? And notice that this is the same thing that we started with. So that's f of x. So we know that this is an even function. Is that okay with everybody? So the even one should be easy to tell because you're just going to end up back with what you started with, right? Let's do another. So again, either way, I'm going to start with g of negative x. So that tells me I'm going to plug negative x in for x. If I take a negative and raise it to the third power, what do I get? A negative. And then 3 times negative x is just negative 3x. Everybody's okay with that? Notice there, if I factor a negative out, I have the original again, right? So this is just equal to negative f of x. Therefore, It's odd. Is that okay? If I'm going too fast, or if you need me to slow down or re-explain something or come in with some more detail or you have some follow-ups or some clarifications, stop me, ask. That's what this time is for. It's totally fine to do that. Alyssa, looks like you're waiting. Go ahead.
I'm just confused how you got the odd from. Like, how does that, how do you know that's not even the odd?
Yeah, so if I look at the definition here, odd, when I start with f of negative x, I need to get negative f of x, right? So I start with negative, or f of negative x, right? I plug that in. I get this. If I factor the negative sign out, this part was just f of x, so I have negative f of x, right? Is that okay? Let me illustrate it this way for you. That might be a little bit, it loses the elegance of having it just like one line straight across. Negative g of x would be this, right? You agree with that? And g of negative x would be this, right?
Yeah.
So they're the same thing, right?
Yeah.
So they're odd.
Alright, thank you.
Does that feel a little bit clearer if we would write it that way?
Yes.
And if that works for you, that's fine. It doesn't have to be in one line. You can certainly approach it from that way, especially if you're like, you know, if it makes more sense to you do it that way, do it that way. If it's more clear, it's more clear. It's equally good. Okay? You know, you lose a little bit of style points for using 2 lines instead of 1, but like, I don't think we really care too much about style points. I'm not grading on style points anyways. You know what I mean, guys? Because what the heck does that mean, the style point? How am I going to assess that? Okay. H of x equals 4x squared minus 3x plus 9. Again, either way I'm going, I need to know h of negative x, whether it's odd or even, right? So we'll go ahead and do that. So if I simplify this, I get that. Is that okay? If I compare this to h of x, those are not the same, right? I got some signs that are wrong. You guys agree? So it's not even. Okay? Well, if I factor a negative sign out, I would have this. And again, this is not that, right? So it's also not negative h of x. So what do we have here? It's neither. How much time do we have left? We got like 10 minutes or something? Oh, we have like 20 minutes left. Great. We'll do some extension on this because I only really wanted to do 2 sections today because I don't want to have add a bunch more homework. But there's some neat stuff we can talk about still with this. So, John.
So like the basic process is you look for f of negative x for first.
Mhm.
And then if it's not that, you have to factor out the negative to see if it's negative at the
Mhm.
it's neither then.
And if it's not that, then it's neither. Yep, exactly. Yep, that's the idea. Well put. Okay. So let's look at these 3 examples we did and see if you notice anything that we can make a conjecture about. So let me just re-summarize down here. That'll be easier than scrolling back and forth and back and forth and back and forth. So this was our result. Right? This was the result that we got from our examples. Everybody okay with that? I just recopied it. If we look at these functions, f of x, g of x, and h of x, what kind of function were these in all 3 places? What kind of functions were they? Like last year in your algebra class, you would have called these polynomials, right? Everybody good with that? Okay. What do you notice about these polynomials? Because really, in this situation, we're asking whether a polynomial is an odd function or an even function or neither function. You could do this on site without actually having to to prove it, you still need to do the proof. But like you should be able to look at this and know whether they're going to be odd or even. You don't know yet because we haven't figured it out, but you can just look at these and be able to tell. John, do you have an idea?
For the first 2, if the exponent is like attached to the x.
Okay. So here, this is an even exponent, right? But the exponent on the 1 is a first. So maybe the exponent isn't what we're looking for, but something related to the exponent, specific to polynomials. What piece of vocab is related to the exponent of a polynomial, but is just a little bit different? Yes, sir. Tanner, right? Degree, yes. What is the degree on 1? It's 0, because really we can always tack on an x to the 0, which is 1 after all these things. So this is an even degree, and this is an even degree, and that's an even function. Here, this is an odd degree. That's an odd degree. We have an odd function. Here we have an even degree, an odd degree, and an even degree, and we have an either. So what would our conjecture be? Yeah. The sum or difference of even degree polynomials is an even function. Everybody agree? That's kind of what we're saying here. Similarly, the sum of odd degree polynomials is going to be an odd function. And if you have some difference, if you have an odd plus an even, that's an either. Everybody agree with that? So let's extend that a little bit. Okay. Yeah. So let's make this a little bit more general. So what can we say about a function that is an even degree monomial? It is always an even function, right? Everybody agree with that? should be clear as to why, right? If you plug negative x in, it just, the even exponent nukes out the negative and you're left with what you started with. You know what I mean? So what if I make this a little bit more general and say even functions? Do you think that that's going to be true? That the sum of even functions is also an even function? Let's try to prove it, right? Let's say we have f of x is equal to, like g1 of x plus g2 of x plus, gn of x, where g sub I of x is an even function for I equal 1 to n. That's what we're saying, right? Is that if I add up a bunch of even functions together, I should end up with an even function again. We'll start our proof the same way we would before. So we'll do that. And what's g1 of negative x have to equal? What do we know about g1 of x? Since it's even, it's just g1 of x, right? g2 of negative x is also even, so it just equals g2 of x. And all the way down. So of course that's got to be even, right? Does that make sense? We see how it's just still basically the same proof as what we did before. It's now just like really general, right? Instead of using a specific polynomial with specific terms, we just called them even functions and we gave them like a generic name. But the same thing kind of holds true. This was like the same thing as if that we had here, where like g1 is x to the fourth and g2 was 1, right? It's the same proof that we did before, just we've, instead of doing something specific, we did like really general. Would this change appreciably if g1 was odd? What do you think? Would this work for odd functions as well? If all these g's were odd? Let's see. So we have our function that's the sum of odd functions, and we want to see is that odd, right? Well, do it the same way, or start it the same way as we started the other ones. Oops. Now, since g1 of negative x is odd, what does that have to equal? Very good. And similarly all the way down, right? So since we have a negative sign in front of each of our g's, we can factor that -1 out. So we just have negative f of x. So it's odd. So the sum of odd functions is also odd. Everybody's okay with that? And that feels like a good place to stop now that I killed a little bit of time and we did a little bit of extension. The stuff that we just did here at the end in this last 10 or 15 minutes where we proved these things were like even more generally were true would not be something I expect for you to repeat on a test or a quiz or whatever. But it's nice information to have, right? It certainly makes doing the other proofs easier if you can look at it on site and go, that answer, I know that's going to be odd, or I know that one's going to be even, so you can kind of detect if you make a mistake or whatever in the problem. You know what I mean? All right. We're going to add to our homework here. So you can now be able to do 13 through 22. So my plan here is